Imagine walking into one of the world's busiest airports in the early 1990s. Look out across the runway. A Boeing 737 is boarding passengers for another domestic flight. A Boeing 747 is preparing to cross the Pacific. A Boeing 767 is carrying business travelers across continents. A brand new Boeing 777 is demonstrating what the future of aviation looks like. Now look again. Different airlines, different countries, different languages, yet one company connects them all. Boeing. For almost half a century, Boeing wasn't simply building airplanes, it was quietly building the operating system of global aviation. Every day, millions of passengers placed their lives inside Boeing aircraft without giving it a second thought. Pilots trained on Boeing cockpits, engineers specialized in Boeing maintenance, airports designed gates around Boeing dimensions, banks financed Boeing fleets, airlines built entire business models around Boeing aircraft. The deeper you looked, the more Boeing seemed impossible to replace. But Boeing didn't become the world's aviation giant overnight. It earned that position one aircraft at a time. In 1958, the Boeing 707 helped launch the jet age. Flying suddenly became dramatically faster than the propeller aircraft that had connected the world for decades. Airlines could carry more passengers across greater distances in less time, while creating an entirely new expectation for international travel. Then came the Boeing 727. Many airports couldn't accommodate the largest aircraft. The 727 solved that problem. It could serve shorter runways, reach regional cities, and expand commercial aviation far beyond major international hubs. Then Boeing introduced what would become the best-selling commercial aircraft in history, the Boeing 737. Simple, reliable, economical. An aircraft designed to fly the routes airlines operated thousands of times every single day. By now, Boeing wasn't just making airplanes, it was solving one airline problem after another. Then came the gamble that could have destroyed everything, the Boeing 747. No airline had ever operated an aircraft that large. No manufacturer had ever attempted production on that scale. Boeing borrowed enormous amounts of money, constructed what became the world's largest building by volume in Everett, Washington, hired thousands of new workers, and bet the future of the entire company on one aircraft. If airlines rejected it, Boeing might not survive. Instead, the opposite happened. The 747 became an icon. It carried hundreds of passengers across oceans, connected continents like never before, reduced the cost of long-distance travel, and transformed international tourism, business, and global trade. By the time Boeing introduced the 767, then the revolutionary twin-engine 777, the company had achieved almost no manufacturer in history. It had earned trust. Not marketing, trust. When an airline purchased a Boeing, it wasn't simply buying an airplane. It was buying decades of engineering experience, a worldwide maintenance network, thousands of trained pilots, certified mechanics, simulator programs, spare parts warehouses, financing support, operational manuals, engineering documentation, and one of the strongest safety reputations in commercial aviation.
Changing aircraft manufacturers wasn't like changing suppliers. It meant retraining thousands of pilots, replacing maintenance equipment, buying new simulators, stocking different spare parts, rewriting engineering procedures, changing dispatch systems, changing maintenance software, even changing the way crews operated aircraft every day. Switching away from Boeing could cost an airline hundreds of millions of dollars before the first passenger even boarded. That created something far more valuable than market share. It created an ecosystem. Every Boeing aircraft made the next Boeing aircraft easier to sell. Every airline that joined the ecosystem became more deeply connected to it. Every new pilot trained, every maintenance engineer certified, every airport adapted, made Boeing's position even stronger. By the early 1990s, many people believed Boeing had already won. The world's largest airlines trusted it, governments trusted it, investors trusted it, passengers trusted it. Its engineering was admired, its manufacturing was respected, its aircraft connected almost every corner of the planet. If someone had claimed that another manufacturer would eventually overtake Boeing, most industry experts would have laughed. Because across the Atlantic, Europe wasn't building one company, it was attempting something far more ambitious. Several nations, multiple governments, separate aircraft manufacturers, different languages, different political interests, different factories were all trying to achieve one goal: create an aircraft company capable of defeating the greatest aerospace manufacturer the world had ever seen. Its name was Airbus, and almost nobody believed it could succeed.
At first glance, Airbus looked like an impossible idea. Imagine asking 4 different countries, each with its own government, its own aerospace companies, its own engineers, its own factories, its own political priorities, to build one commercial aircraft together. Most people would expect disagreement, delays, cost overruns, and eventually failure. Yet that was exactly the challenge Europe accepted. During the 1960s, Europe still possessed some of the world's finest aerospace engineers. Britain had built successful aircraft. France had world-class aviation companies. Germany was rebuilding its aerospace industry. Spain was expanding its manufacturing capability. But there was one problem. They were all competing separately. Every company designed its own aircraft. Every factory built relatively small production runs. Development costs kept increasing. Sales remained limited. Meanwhile, across the Atlantic, Boeing was spreading development costs across hundreds of aircraft. Every successful program generated more money for the next one. The gap kept growing. European manufacturers slowly realized something uncomfortable. Individually, none of them were large enough to challenge Boeing. So, instead of competing against each other, they decided to compete together. In 1970, Airbus Industry was created, not as one traditional company, but as an industrial partnership. Each country would contribute what it already did best. Britain focused on wings, not by accident. British aerospace engineers had developed some of the world's most advanced wing design expertise. The wing isn't simply where lift is generated. It stores fuel, supports engines, transfers enormous structural loads throughout the aircraft, and determines much of its aerodynamic efficiency. France became responsible for much of the cockpit, forward fuselage, and final assembly. Germany specialized in major fuselage sections, cabin structures, and manufacturing systems. Spain contributed tail structures, composite components, and additional manufacturing capability. At first, the arrangement looked incredibly inefficient. Aircraft sections weren't built in one giant factory.
Instead, entire fuselage sections, cockpit modules, tail assemblies, and wings traveled across Europe before finally meeting in Toulouse. Some traveled by specially modified ships, others by road. Later, Airbus introduced one of the world's largest transport aircraft, the Beluga, designed almost entirely for one purpose: carrying enormous aircraft components between European factories. To an outsider, this looked expensive, complicated, even risky. Why not simply build everything under one roof like Boeing? Because Airbus wasn't optimizing for one factory, it was optimizing for an entire continent. Every participating country invested politically, financially, and industrially. Every government now had a reason to support Airbus. Every factory became part of one much larger production system. Every supplier gained access to future aircraft programs. Europe wasn't just sharing costs, it was sharing survival. Then Airbus made another decision that surprised the aviation industry. Its first aircraft, the A300, would be a twin-engine wide-body. At the time, most airlines believed large aircraft needed 3 or even 4 engines, especially for longer routes. 2 engines seemed too risky. Airbus saw something different. Jet engines were becoming more reliable. Fuel represented one of the largest costs for airlines. Every unnecessary engine meant more maintenance, more inspections, more fuel consumption, and higher operating costs. If Airbus could convince airlines that 2 engines were enough, operating economics could change completely. The engineering challenge was enormous. The commercial challenge was even bigger. Because building a great airplane wasn't enough, Airbus still had to persuade airlines to trust a manufacturer that had never produced a commercial aircraft before. While Boeing wasn't just selling airplanes, it was selling decades of confidence. Airbus wasn't fighting an aircraft, it was fighting trust. And in aviation, trust may be the hardest product in the world to earn.
By the mid-1980s, Airbus had done something many experts believed was impossible. It had proven Europe could build a world-class commercial aircraft. But building an aircraft was never the hardest part. Selling one was. Imagine you're the CEO of a major airline. You need 50 new aircraft. The order is worth billions of dollars. Which manufacturer do you choose? Most people think the answer begins with the airplane. It doesn't. The airplane is only one piece of a much larger system. An airline doesn't simply buy an aircraft. It buys everything that keeps that aircraft flying for the next 30 years. Every new aircraft creates thousands of decisions. How many pilots need training? Will existing simulators still work? Do mechanics already understand the aircraft? Will new maintenance hangars be required? Which spare parts need to be stocked? Can existing airport gates accommodate the aircraft? Will engineers need new certifications? How much fuel will it burn? How often will it require major inspections? How many passengers can it carry? How much cargo fit underneath? How much revenue can each flight generate? One aircraft decision can reshape an airline's business for decades. That is why airlines rarely think in terms of individual airplanes. They think in terms of fleets. Boeing understood this earlier than almost anyone. Its aircraft weren't designed to exist alone. Each new model strengthened the entire Boeing ecosystem. Pilots already familiar with Boeing cockpits could transition more easily. Maintenance organizations expanded existing knowledge. Airlines already owning Boeing aircraft often needed fewer changes throughout their operations. Every successful sale reinforced the next one. This became one of Boeing's greatest competitive advantages.
Airbus understood something equally important. If it wanted airlines to switch manufacturers, building an excellent airplane wouldn't be enough. The entire operating system had to become easier. Training, maintenance, cockpit design, fleet planning, operating economics, everything had to work together. Airbus wasn't simply competing against Boeing's airplanes, it was competing against decades of airline habits. Every pilot trained on Boeing, every engineer certified, every maintenance procedure written, every operations manual already sitting inside airline headquarters. Changing manufacturers meant changing thousands of tiny processes. Each one cost money. Each one introduced risk. Airlines only accepted those risks if the long-term rewards became even greater. That forced Airbus to ask one question that would define the next 50 years. How do we make every aircraft easier to fly, easier to maintain, and easier to integrate into an airline fleet? The answer wouldn't begin inside the engines or inside the wings. It would begin inside the cockpit, and it would completely change the relationship between pilots, computers, and the aircraft itself.
Until now, Boeing and Airbus had been competing using airplanes. From this point forward, they would compete using philosophy. To most passengers, a commercial aircraft is simply a machine that flies from one city to another. To an engineer, every aircraft represents thousands of design decisions. Should the pilot always have the final authority, or should the computer step in when it believes the pilot is making a dangerous mistake? That single question would eventually separate Boeing and Airbus more than any engine, wing, or fuselage ever could. For decades, Boeing believed the pilot should remain the final decision-maker. Its engineers built aircraft that provided warnings, automation, and assistance. But ultimately, if a trained pilot wanted to move the aircraft beyond normal operating limits, Boeing generally believed that authority should remain with the human. The philosophy was simple. Pilots train for years, gain thousands of hours of experience, and should always remain connected to the airplane. Airbus looked at the same problem differently. By the 1980s, computers had become dramatically more powerful. Airbus asked, what if computers could prevent mistakes before they happened? Instead of relying entirely on pilot judgment, the aircraft itself could continuously calculate speed, altitude, angle of attack, bank angle, structural loads, and hundreds of other parameters every second. If the pilot accidentally attempted a maneuver that exceeded safe limits, the aircraft could simply refuse the command. This became known as flight envelope protection. Think of the flight envelope as the aircraft's safe operating boundary. Maximum bank angle, minimum flying speed, maximum structural loads, maximum pitch. Airbus computers constantly monitored those limits. If a command exceeded them, the system intervened. The pilot was still flying the aircraft, but inside carefully protected boundaries. Boeing engineers respected automation, but they worried about something different. What happens if the computer is wrong, or if sensors fail, or if pilots lose awareness because automation performs too much of the flying? Their philosophy remained centered on preserving pilot authority. Neither approach was irrational. Both emerged from decades of engineering experience. Both had strengths. Both introduced different risks. The differences extended far beyond software. Look inside the cockpit. Most Boeing aircraft retained the traditional control column, a physical yoke directly in front of each pilot. Airbus introduced a side stick controller, smaller, lighter,
mounted beside the pilot instead of directly ahead. The change wasn't cosmetic. Removing the large control column improved instrument visibility, created more cockpit space, and reflected Airbus's belief that pilots were increasingly managing sophisticated flight systems, not simply moving mechanical control surfaces. Then came another major difference: fleet commonality. Airbus designed its aircraft family so pilots could transition between different Airbus models with significantly less retraining than moving to an entirely different manufacturer's aircraft. Cockpit layouts remained remarkably consistent. Flight computers behaved similarly. System logic stayed familiar. For airlines, that meant lower training costs, greater scheduling flexibility, and easier long-term fleet planning. Boeing also pursued commonality within its own aircraft families, but Airbus built the concept into nearly every aspect of its product strategy. It wasn't simply designing airplanes, it was designing one connected family. To passengers, these differences were almost invisible. To airlines, they could save millions of dollars every year. To engineers, they represented two completely different ways of thinking about aviation. One philosophy trusted the pilot first, then the computer. The other trusted the computer to help protect the pilot. For years, both systems appeared remarkably successful. Neither company could prove its philosophy was truly superior. But eventually, the industry would face situations where those philosophies would be tested under extraordinary pressure, and the consequences would reshape commercial aviation forever.
For decades, Boeing's greatest advantage wasn't a single airplane. It was the way the company built airplanes. Aircraft development had always been one of the most difficult engineering challenges on Earth. A modern commercial airliner contains millions of individual parts, thousands of suppliers, hundreds of specialist manufacturing processes, complex avionics, hydraulic systems, electrical wiring stretching hundreds of kilometers, composite materials, software, engines, landing gear, flight controls, cabins, fuel systems. Every component must arrive at exactly the right time, in exactly the right sequence, because a delay in one section can stop work across an entire production line. For decades, Boeing controlled almost every critical part of that system. Its engineers designed the aircraft, its factories assembled major structures, its managers coordinated suppliers. Its experienced workforce solved problems long before customers ever saw them. The company wasn't simply manufacturing airplanes, it was controlling one of the world's most sophisticated industrial ecosystems. Then, everything began to change. In 1997, Boeing merged with another American aerospace giant, McDonnell Douglas. At first, the merger appeared logical. It would create a stronger aerospace company, broader product lines, and greater financial strength. But inside Boeing, something more subtle was beginning to happen. The company gradually shifted from asking, "How do we build the world's best airplane?" toward another equally important question: how do we build it more efficiently? Efficiency isn't a problem. Every manufacturer pursues efficiency. The challenge is knowing where efficiency creates strength and where it quietly creates risk. That question became critical during Boeing's next revolutionary aircraft, the 787 Dreamliner. Unlike previous Boeing programs, large sections of the aircraft would no longer be built primarily inside Boeing factories. Instead, major fuselage sections, wings, doors, electrical systems, and countless other assemblies would arrive from suppliers across the world. Many sections were delivered almost completely assembled. The idea sounded brilliant. Suppliers would invest their own money, manufacture complete sections, and deliver them ready for final assembly. Boeing expected faster production, lower costs,
less capital investment, and reduced financial risk. On paper, the model looked revolutionary. Reality proved far more complicated. When major aircraft sections arrived, many weren't actually ready. Some contained manufacturing defects, others had incomplete wiring, missing fasteners, poorly fitting components, or engineering work that still needed to be completed. Instead of simply joining finished sections together, Boeing engineers found themselves completing unfinished work inside the final assembly factory. The aviation industry calls this traveled work. Problems that should have been solved earlier traveled downstream into later stages of production. Every hour spent correcting unfinished work slows the entire production line. Workers begin performing tasks out of sequence, schedules become unpredictable, costs increase, finished aircraft remain inside factories longer than planned. The disruption spreads. One supplier affects another. One incomplete fuselage delays engine installation. Engine installation delays systems testing. Testing delays delivery. Delayed deliveries delay airline schedules. Airlines postpone fleet expansion. Cash remains trapped inside unfinished aircraft. The problem is no longer one factory. It becomes an entire industrial system struggling to stay synchronized. Airbus also depended on suppliers. It also built aircraft across multiple countries. It also faced production challenges. The difference wasn't whether outsourcing existed, it was how much control remained over the complete production system. As Boeing pushed more responsibility outward, the company gradually became more dependent on every supplier executing perfectly. And aircraft manufacturing almost never works perfectly. Tiny deviations, measured in millimeters, can affect sections stretching more than 60 meters long. One missing bracket, one incorrectly drilled hole, one delayed wiring harness can ripple through months of production planning. For years, Boeing had mastered those relationships. Now, the company was trying to coordinate one of the most globally distributed manufacturing systems ever attempted in commercial aviation. It wasn't failing because engineers had forgotten how to build airplanes. It was struggling because the industrial machine itself had become dramatically more complicated, and the consequences were only beginning to appear.
By the end of the 2000s, Boeing still had one of the strongest product portfolios in aviation, but Airbus had found an opening. In 2010, Airbus announced the A320neo. The name stood for New Engine Option. On the surface, it looked like a relatively small upgrade, a more fuel-efficient engine, improved aerodynamics, lower operating costs. But airlines immediately recognized something much bigger. Fuel is one of the largest operating expenses in commercial aviation. Saving only a few % on every flight across hundreds of aircraft over decades of operation could save an airline hundreds of millions of dollars. Orders flooded in. Airbus wasn't asking airlines to learn a completely new aircraft. The A320neo remained part of the same Airbus family. Pilots required minimal additional training. Maintenance systems remained familiar. Airlines could modernize their fleets without rebuilding their entire operation. Boeing suddenly faced one of the most important strategic decisions in its history: build an entirely new narrow-body aircraft or upgrade the existing 737 once again. A completely new aircraft would likely require close to a decade of development, billions of dollars in investment, new certification, new pilot training, and Boeing risked losing customers while waiting. Instead, the company chose to evolve the aircraft airlines already trusted, the Boeing 737 MAX. At first, the decision appeared commercially brilliant. Airlines could continue flying a familiar aircraft, pilots could transition quickly, maintenance organizations already understood the platform.
The supply chain already existed. Production lines were already operating. The airplane could reach the market much faster. But there was one engineering problem. The new engines were much larger than the previous generation. The original 737 had been designed decades earlier with relatively low ground clearance. Simply placing larger engines beneath the wings wasn't straightforward. Engineers repositioned the engines higher and farther forward. That solved one problem, but introduced another. Under certain flight conditions, the new engine position slightly changed how the aircraft naturally behaved. This did not make the airplane unflyable, but Boeing wanted the MAX to feel as familiar as possible for pilots transitioning from earlier 737 models. The solution became a software system called MCAS, the Maneuvering Characteristics Augmentation System. MCAS was designed to automatically move the horizontal stabilizer under specific conditions when sensors indicated the aircraft was approaching a high angle of attack. An angle of attack measures how steeply the wing meets the airflow. If the angle becomes too great, the wing can lose lift and enter an aerodynamic stall. MCAS was intended to reduce that risk by automatically trimming the aircraft's nose downward when it detected those conditions. The concept itself wasn't unreasonable. Modern aircraft rely on many automated systems. The problem wasn't that automation existed. The problem was how this particular system became integrated into a much larger chain. During certification, the aircraft was marketed as requiring minimal additional pilot training compared with earlier 737 models. Many airlines welcomed that approach because additional simulator training costs both time and money. MCAS also depended heavily on information from a single angle of attack sensor during its original design. If that sensor transmitted incorrect information, MCAS could activate when it wasn't actually needed. In October 2018, Lion Air Flight 611 crashed into the Java Sea. Investigators found repeated nose-down trim commands as pilots struggled to understand the aircraft's behavior. Less than 5 months later, Ethiopian Airlines Flight 302 crashed shortly after takeoff under remarkably similar circumstances. In total, 346 people lost their lives. The world responded immediately. Aviation authorities grounded the Boeing 737 MAX across much of the globe. Production slowed dramatically, delivery stopped. Airlines faced enormous disruption. Investigators examined every layer of the system: engineering decisions, certification, pilot training, company processes, regulatory oversight, software design, documentation, communication. The tragedy wasn't caused by one mistake. It emerged from multiple decisions made by different people across different organizations at different times. Each decision appeared manageable on its own. Together, they produced one of the most significant crises in modern aviation. For the first time in generations, the trust Boeing had spent decades building was shaken across the world. When the Boeing 737 MAX returned to service, the crisis wasn't over. It was entering a new phase. Boeing had redesigned MCAS. Pilots received additional training. Aircraft were inspected. Regulators reviewed the changes. Gradually, the MAX returned to airline fleets around the world. But trust is very different from certification. Certification can be restored through engineering. Trust must be rebuilt through years of consistent performance. And Boeing wasn't finished facing difficult questions. While the company worked to stabilize the MAX program, other production challenges emerged. On the 787 Dreamliner, manufacturing inspections identified quality issues involving fuselage joints and production tolerances. Aircraft deliveries slowed. Additional inspections became necessary. Production rates were reduced while engineers verified structural integrity and manufacturing records. Then, in January 2024, another event captured worldwide attention: Alaska Airlines Flight 1282. Shortly after departure, a door plug separated from the aircraft. The airplane landed safely, but investigators quickly discovered something deeply concerning. The problem wasn't caused by weather, or pilot error, or engine failure. Investigators found that retaining bolts designed to secure the door plug had not been reinstalled after manufacturing work. The National Transportation Safety Board later concluded that Boeing failed to provide adequate training, guidance, and oversight necessary to ensure manufacturing personnel correctly completed the work. For Boeing, the incident represented something larger than one aircraft. It suggested that manufacturing discipline, documentation, inspection, and quality control still required fundamental improvement. The Federal Aviation Administration responded by increasing oversight. Production of the 737 MAX remained capped while Boeing demonstrated improvements to manufacturing quality. Meanwhile, Airbus continued expanding. The A320neo family became one of the most successful commercial aircraft programs ever built. The A321neo proved especially valuable for airlines seeking longer range and greater passenger capacity without moving to a wide-body aircraft. Airbus delivered more commercial aircraft than Boeing in recent years. Its backlog reached record levels. But the story doesn't end with Airbus becoming perfect. The A380 never achieved the commercial success Airbus had hoped. Engine shortages have slowed deliveries. Global supply chain constraints continue affecting production. Even the market leader still faces enormous industrial challenges. Commercial aviation has never rewarded companies that stop improving. Now another challenger is beginning to emerge: China's COMAC. Just as Airbus once challenged Boeing, COMAC hopes to challenge both Boeing and Airbus in the decades ahead. History is beginning another cycle. So, did Boeing collapse? No. Boeing still designs extraordinary aircraft. It remains one of the world's most important aerospace companies. Its engineers continue building airplanes that connect millions of people every year. Its defense, space, and commercial businesses remain critical to global aviation. But something did change. For much of the 20th century, Boeing defined the direction of commercial aviation. Today, it is rebuilding production, rebuilding quality systems, rebuilding customer confidence, and rebuilding the trust that once made its name almost unquestionable. Perhaps that is the real lesson. Industries rarely change because one company suddenly becomes incompetent. They change because the systems that once created success become harder to manage as technology, competition, supply chains, and customer expectations evolve. Boeing didn't lose the skies because it forgot how to build airplanes. It lost its unquestioned leadership because maintaining one of the world's most complex industrial systems became more difficult than creating it. Airbus spent 50 years building a system prepared for the future. Boeing now faces the challenge of rebuilding the system that once made it unstoppable. Whether it succeeds will shape commercial aviation for decades to come. Because history has already shown one thing: in aviation, no empire owns the skies forever. If you enjoyed this documentary and want more deep dives into the business systems, engineering decisions, and hidden mechanics behind the world's biggest corporate successes and failures, subscribe to ApexFall. There are many more stories awaiting to be uncovered.